In this video, I'm going to be focusing on a few practice problems that have to do with Gibbs free energy. And so one thing I want to point out before I even begin on these problems is you need to understand and know the difference between delta H, delta G, and delta S. And so remember, delta H, or the enthalpy of your reaction or of your compound, has to deal with how much energy is going to be released or absorbed in order for these reactions to go to completion. And so remember, enthalpy, or delta H, only has to do with the thermochemistry, or has to do with the fact that these things are either going to be exothermic or endothermic reactions or formations or decompositions or what have you. Whereas delta S, or entropy, has to do with the chaos of the world. It has to do with the ways that you can distribute out your energy throughout all these microstates. And so remember the huge difference between enthalpy and entropy. And then to make things even more difficult, then they throw in delta G. And so delta G, or the Gibbs free energy, or standard Gibbs free energy, has to deal with if these things are going to be spontaneous or non-spontaneous. And so normally you need to have a combination of at least two of these variables in order to figure out if your reaction is going to be spontaneous and exothermic, or exothermic and non-spontaneous, or endothermic and spontaneous, or however way you're going to look at it. Normally, delta H by itself will not tell you anything about the spontaneity. Delta G by itself will not tell you anything about if it's going to be exothermic or endothermic. You need to have some type of combination of these variables in order to basically tell you the whole story about how these reactions are going to occur. And so that brings us to actually looking at these practice problems. And so there's actually a couple different ways that you can calculate your free energy. In addition to that, it depends on what type of free energy they're asking about in order to depend on or determine which equation you're going to be using. And so for this particular problem, I give you a whole bunch of information, and I'm asking you to determine the standard free energy of the following reaction under standard conditions. And so the great thing about standard conditions is all these values that have the degree signs on them, or the delta HF and the delta GF and the delta S I have here, all these have degree signs on them. And so that F on the enthalpy in the free energy refer to formation. And so all I'm telling you is that the HCN, or the delta H, standard delta H of formation, is 105 kilojoules per mole. And so that delta H is just basically saying, in this case, how much energy is going to be released or absorbed whenever you form HCN. Please note, and again, this goes back to previous chapters, your O2 does not have a delta H formation. The reason for that is because O2 always exists as a gas. No energy is going to be absorbed or released when oxygen becomes oxygen because it's already oxygen. And the same deal with N2 as well. And so if I ask a question like I do here, and I mention the fact that all this stuff is under standard conditions, you can use these standard enthalpies and standard free energies and standard entropies in order to solve for things under standard conditions. And so for this one, we can use a very simple equation, and I say simple just because we've seen it in one form or another at least 3 times in the past. But you can use Hess's law and determine the delta G, again, standard delta G of the reaction, by looking at the standard delta G's of all your products as well as all the standard delta G's of your reactants and subtracting the two. And so here this chemical reaction gives you the products and gives you the reactants. And I also tell you all the standard delta G's of all your products and reactants, and I'll even circle them right here, or I guess box them, so now you can see what I'm talking about. And so when you set this thing up to solve for the standard delta G, you can use the standard delta G of formations of all your products and reactants and just plug them in accordingly. And so the main issue that I've seen a lot of students run into with this in the past is you need to take into account that each of these delta GFs, or standard delta GFs, is in the form of kilojoules per mole. And so you need to remember that if you have more than 1 mole, you have to account for that fact. And so whenever you have 4 HCNs and 5 O2s, you need to multiply these values times that number of moles in order to get the correct answer here. And so just breaking this down and again, kind of follow my color-coded system here. All of my products are my H2O, my CO2, and N2, the sum of all of their delta G's, and then do the same thing. Take the sum of your 4 HCNs and your 5 O2s and subtract the 2. And so here, as I stated, you just need to pay special attention to the number or the coefficient or the number of moles of these products and reactants. And so when you work this out, you're going to have 2 times the standard delta G of your water because you have 2 waters in your balanced chemical formula. You need 4 times the standard delta G of your CO2, and you need 2 times the standard delta G of your N2 in order to keep these coefficients straight here. And then you're going to take all of that and you're going to subtract 4 times the standard delta G of your HCN plus 5 times the standard delta G of the O2, just because your coefficients state the fact you need to keep those ratios the same. And so after that is nothing more than a plug and chug problem. But the main thing you have to remember here is to keep those negative values negative if it calls for it inside the table or whatever values are going to be given to you on the exam or assignment. And so here, plugging these things in, your standard delta G of H2O is negative 228.6. Your standard delta G of your CO2 is your negative 394.4. Standard delta G of the N2 is 0. And then on the other side, or your reactant side, you have your standard delta G of the HCN is 121 kilojoules, and your standard delta G of your O2 is going to be 0. And so plug all those values in, making sure to account for the negatives, making sure you have your parentheses in the right spots, and so you're not subtracting when you're not supposed to be. Plug it all into your calculator, and you can solve for the standard delta G of this reaction comes out to negative 2514.8 kilojoules. And so one thing we can infer about this actual chemical reaction is that whenever we look at the negative 2514.8 kilojoules, it's telling you that this reaction is pretty spontaneous. And remember, if you have a negative delta G, you're looking at a spontaneous reaction. If you're looking at a positive delta G, you're looking at a non-spontaneous reaction. And if your delta G is equal to 0, you're looking at something that's pretty dang close to equilibrium. And so now we can kind of take a look at another type, or I guess another version of this question, in which I'm going to now change things from standard conditions, and I'm going to give you a condition that is no longer standard. And so I give you the same exact table, same exact chemical reaction, and now I'm telling you that I want to know the standard free energy of the following reaction at 35 degrees Celsius. And keep in mind, 35 degrees Celsius is not standardized. And so we kind of go through and do this. We can no longer use our standard Gibbs free energies because, again, that's not really going to be what we're looking for. And so in order to do something a little bit different, we're actually going to have to use kind of a combination of a couple different aspects here. And so there's this fancy smancy equation, or the relationship between all your delta H's and your delta S's and your delta G's if all of them are in their standard form. And we have a way to relate all this stuff to our temperature. And again, if you want to know something that is not in a standard state, first you have to kind of figure out all the information you're given in the form that it's given, and then manipulate it in one form or another. And in this case, that temperature is really the only thing that's throwing all this stuff off from the standard states. And so using this equation, you can use your standard enthalpies, you can use your standard entropies, you can solve for your standard Gibbs free energy, and then relate everything back to one another using that temperature change, or sorry, not change, but that temperature that's going to be different than what it would be a standard state. And so for this one, we need to learn something about our standard enthalpy and our standard entropy. And so again, we can't use our standard G or delta GF anymore because they're not going to be really valid in this situation. If we know something about our delta H, again, using the same rules that we've done in the past, the same kind of relationship, using Hess's law. If we know the standard delta H's of all of our products and reactants, we can solve for the standard delta H of our reaction. So using the same exact setup, except now you're changing all your G's to H's, but you're still looking at the sum of all your standard delta H's of all your products, minus the sum of all the standard delta H's of the reactants. So you're still using the same coefficients. There's still 2 waters, there's still 4 CO2s, there's still 2 N2s, there's still 4 HCNs, and there's still 5 O2s. The only difference now is you're using these values instead of the delta G's, because right now we're solving for the standard enthalpy of the reaction. And so plugging all of these values in, making sure you, again, still use the appropriate negative signs where they're needed. And so you just plug in the values of the standard delta H's of your H2O, your CO2, your N2, HCN, and O2. Please note, very similar to the the delta G's, you have a standard enthalpy of formation of 0 for both your N2 and your O2. And so now we know our delta H's. Do the exact same thing, but now we're going to be looking at our delta S's. And so using Hess's law and all the same exact setup that we've seen many, many times in the past, you have the reaction is going to be products minus reactants. And so using the same coefficients, using the same setup, but now we're using these values instead of your delta G's or your delta H's. But you're still doing 2 of your waters, 4 of your CO2s, 2 of your N2s, 4 HCNs, and 5 O2s. But now using these values, plug them all into your equation, you should get 139 joules per Kelvin. And so I stated that relationship here because you need to understand the fact that these values given in this table for enthalpy and for free energy, the values are in kilojoules per mole. That entropy, remember, this is kind of talking about how many different places you can spread out or how many different microstates you can spread out your energy in these kind of compounds. And so it's always going to have some relationship to temperature as well, which is lucky for us because that's what we wanted to get rid of is the temperature. And so here you need to make sure that your delta H is in kilojoules and your delta S is going to be in joules per Kelvin because that's the way that these things are ran out for you. And so I should note that, again, we kind of got rid of our per moles because we were multiplying all of these values times the actual moles of the complexes in the chemical formula. And so if we want to solve for our standard free energy of the reaction, we can use the standard enthalpy of a reaction we just solved for and the standard entropy of reaction that we look for. And I'm telling you, this stuff is at 35 degrees Celsius. So the very last thing you need to pay attention to, and again, shouldn't be brand new if you've ever done a chemistry class before in your life, is temperature needs to be in Kelvin. We know that because our entropy is in terms of Kelvin. And so plug all our values in, making sure to make the correct changes where need be. And so our delta H still is going to be in our kilojoules. Our temperature needs to be converted into Kelvin, and so it's going to be your 35 degrees Celsius plus the 273.15 in order to reach your Kelvin unit. And then your delta S needs to be converted into kilojoules because I'm asking for the delta H, and typically those are going to be given in kilojoules. You could go the other way around. You can change your delta H into joules, but this way I'm just solving it for one unit and I'm keeping it in kilojoules. And so making sure everything is in the straight form, kilojoules minus kilojoules, you're not kind of screwing with or trying to do weird math there. And so plug all these values into your calculator correctly using the correct negative signs where need be, and you should end up with negative 2520.4 kilojoules. If you compare this value to the value that we had previously, one of these things are under standard conditions, it's not too far off. The main reason for that is because, again, standard conditions is roughly around like room temperature depending on what kind of things we're talking about here. And so 35 degrees Celsius is not too far off from that. And so this last problem actually kind of switches things up a little bit here. And so in the previous two questions, I asked about the standard free energy. This one, I'm not interested in the standard free energy as much as I am about just the normal everyday Gibbs free energy. Meaning the fact that I'm not specifying all the values and all the compounds are going to be in the standard form. And so I want to know the Gibbs free energy of a mixture of 2 atmosphere of NH3, 1 atmosphere of O2, 1.5 atmosphere of H2O, and 1.2 atmosphere of NO at 25 degrees Celsius. And so one thing, again, you should kind of know here is I'm asking about Gibbs free energy and not standard Gibbs free energy. Other thing is I'm giving you pressures or partial pressures here. Anytime you see partial pressures or you see things given to you in terms of concentration, you should have a red flag go off in your brain saying something about Q's and K's. And so remember, Q's can be solved for whenever you're talking about any reaction that is not at equilibrium. K is specific for equilibrium. And so that Q, for those of you guys who are drawing a blank, that is the reaction quotient. And so you're going to be taking this case, you're going to be taking the partial pressures of your products divided by the partial pressures of reactants. The main thing you have to remember, though, is all of those coefficients become exponents to those pressures or to those concentrations. And so if you know the relationship between Q's and you know the relationship between your standard free energies, you can use this other equation, or delta G equals your standard delta G plus RT times the natural log of Q. And so, great thing about this equation is we've done all this stuff before. You just have to remember how to plug these things in correctly in order to get the variables that you need to solve for. And so, standard delta G, same thing. You should hopefully by now start seeing kind of common rhythm here. But your standard delta G of the reaction is still going to be the sum of your standard delta G's of your products minus the sum of the standard delta G's of the reactants. Using the coefficients in your balanced chemical equation, you have 6 waters, you have 4 NOs, you have 4 NH3s, and you have 5 O2s. So using those coefficients in order to calculate for the number of moles per kilojoule, or kilojoule per the correct number of moles per se, sorry. And then again, plugging them in, you have your negative 228.6 is going to be the standard delta G of formation of your water. The 86.6 is the standard standard free energy of formation of the NO. And then negative 16.4 is the standard free energy of formation of the NH3. And 0 is still there for your standard free energy of formation of your O2. Plug those values into your calculator, making sure to use the correct negative values where appropriate, and you end up with negative 959.6 kilojoules as the standard free energy of the reaction. And again, if you stopped right there, you would have solved for the standard free energy, but we're not talking about this stuff in standard form. One, I'm telling you 4 different pressures, which is not standard. I'm also telling you stuff at 25 degrees Celsius, which is not standard. And so solving this is going to give you the standard free energy, but not the free energy in which the reaction I'm focusing on. And so the next thing here is once we have this standard free energy reaction, we need to figure out Q. And so Q, again, back in the previous chapters, you have to remember that Q is going to be, in this case, since we're given partial pressures and not concentration, still going to be set up the same way. You're going to be taking your products over reactants. You just need to remember that 6H2O becomes the partial pressure of your H2O raised to the power of 6. You have 4 NOs, and so you need to make sure that your partial pressure of NO is raised to the power of 4. Similarly with the other two, or the reactants on the bottom, you have 4 NH3s, and so the partial pressure of NH3 needs to be raised to the power of 4. And you have 5 O2s, and so the partial pressure of your O2 needs to be raised to the power of 5. Plug in the values in the way that the problem states. You have 1.5 as the atmosphere of your water. You have 1.2 as the atmosphere of your NO. You have 2.0 as the atmosphere of your NH3. And you have 1.0 as the atmosphere of your O2. Plugging the values in using the correct, again, the superscripts or the correct exponents. And you end up with a Q of 1.476. Remember, Q's don't have any units. They are just going to be relationships or ratios. And so, now that we know our delta G, or standard delta G of the reaction, we know the Q of our reaction, we can just plug them in. R is always going to be 8.314 joules per mole Kelvin. Your temperature is going to be your 25 degrees Celsius plus the 273.15 in order to get into Kelvin. And the other thing is kind of similar to what we talked about previously. In this situation, because your values are going to be given in joules here, I just kind of kept everything, or sorry, not your values. Your R is in terms of joules. I just converted my delta G into joules per mole before I did the reaction, or sorry, before I did the calculations. You can switch it right back into it at the end, which I also do. And so when we go through and do this, the other thing I have to kind of point out is for my standard free energy that I calculated, or typed out negative 959.6 kilojoules. And so whenever I plug it into this reaction, or for the delta G, I plug it in as kilojoules per mole. The reason for that is because this problem is specifying per mole of a substance because we are using R, which has per mole. Whenever I saw for the delta G of reaction earlier, I was just kind of talking about it's taking this much energy for this reaction to be released or absorbed or spontaneous and all that stuff. And so it all kind of depends on how the question is phrased and what you're actually asking for on if you're going to use kilojoule or kilojoules per mole. Please note, on any multiple choice question, you're probably not going to have too many options between the same value with kilojoules and as one answer and kilojoules per mole with the other one. But I just want to draw your attention to it just so you don't ask the question of why at the very end I have my answers in joules per mole or kilojoules per mole. And so here, as I kind of stated, I converted my standard free energy into joules before I kind of did the math. So at the very end, I just divided by 1,000, and I end up with negative 958.6 kilojoules per mole. Hopefully this helps you out a little bit more, and I'll be posting more videos here in just a little while.